Hi, for my protein project, I'm going to be presenting this to my friend who is an elementary school teacher. I'm going to be using some analogies to explain why mutations or typos in our bodies can cause a rare condition called CAFI disease. CAFI disease is a rare condition that mostly affects infants. It causes painful swelling of the jaw, shoulders, collarbones, and long bones because the body reacts to a mutation in collagen by growing extra bone. Understanding the protein behind it, which is collagen in this case, helps explain why this happens. So the protein we're going to be looking at today is called type 1 collagen. It's the most abundant structural protein in our bodies. So you can think of it as the glue that holds our bodies together. It forms strong fibers that give skin, bones, tendons, and ligaments strength and flexibility. Collagen is made inside the cell in a part called the rough endoplasmic reticulum, or RER, which you can imagine as a protein factory assembly line. After the protein is built, it travels to the Golgi apparatus, which you can think of as the packaging and shipping department. Then the collagen is secreted into the space between cells, which is called the extracellular matrix, which acts as the scaffolding to hold tissues together. This process mainly happens in connective tissue cells called fibroblasts, which produce most of the collagen in skin, tendons, and bones. So here is the healthy model that I made for my protein, which is collagen. So as you can see, there are two teal pipe cleaners in this model and one dark blue. So the two teal represent the alpha 1 chain in collagen, and the dark blue, which is there's only one of those, that represents the alpha 2 chain in collagen. And then there's three different colors of beads, which are representative of amino acids in the makeup of collagen. So the yellow represents glycine, the pink represents arginine, and then the purple represents proline. So in a healthy protein, the amino acid arginine, which is the pink bead here, plays a key role in stabilizing collagen. Arginine is large, polar, and positively charged, allowing it to act as a magnet along the collagen chain. Because of its positive charge, it can form ionic bonds with negatively charged molecules, helping the protein maintain its shape. Its polarity also allows it to form hydrogen bonds with water or other polar amino acids. So now we're going to be looking at the protein structure levels using the model that I made for collagen. So first we have the primary structure, which is also called 1 degree, and that is going to be pertaining to the beads on each of the pipe cleaners, showing the sequence of amino acids, which are yellow, pink, and purple. This is like the protein's chemical code telling the cell how to build it. And so next we have the secondary structure, or 2 degree, and that's twisting a single teal pipe cleaner, which creates a spiral called a helix, which is a local shape along the chain. So next we have the tertiary structure, which is also 3 degree. This is the overall 3D shape of the single chain as it folds. So while the secondary structure is just a small spiral, the tertiary is the whole folded strand together. So we would be looking at a whole helix of one of the alpha chains here. And then lastly, we have the quaternary structure, which is 4 degree. This occurs when all three chains twist together into a triple helix, as you can see looking at the model as a whole. You can think of this as like a 3-stranded rope, which is stronger than any single strand alone. So now I'm going to be discussing the mutated model of my protein. So the mutation in CAFI disease is called R836C, which means that the amino acid arginine, the pink beads, is replaced by cysteine, the green here, at position 836 in the alpha 1 chain of collagen. So cysteine is polar but uncharged, and it has a sticky sulfur group in its side chain. Unlike arginine, which acts like a friendly magnet to organize the strands, cysteine can form abnormal disulfide bonded dimers, as you can see here, with other nearby collagen molecules. These extra bonds cause the collagen strands to clump together and disrupt the formation of the proper triple helix structure. Because of this, the collagen protein has less normal function. It cannot form the strong organized fibers needed to support tissues, essentially. So as a result, the cell's protein factory, the RER, as we discussed earlier, becomes backed up with misfolded proteins, creating stress inside the fibroblast cells. At the organism level, the body responds by forming extra bone, leading to painful swelling of the jaw, collarbones, and long bones in infants. Adults who had CAFI disease as babies may later experience loose joints, weaker connective tissue, or other bone abnormalities. While this physical model helps visualize the collagen structure and shows where the mutation occurs, it does have several important limitations. First, it cannot show the molecular interactions that actually hold proteins together, such as hydrogen bonding or ionic bonding. Second, the bead size and scale are inaccurate. In real proteins, amino acids vary in size. Specifically, glycine is much smaller than the other amino acids that I used in my model. Finally, the model cannot demonstrate the biological effects of the mutation, such as inflammation, abnormal cell signaling, or extra bone growth, which are critical to understanding how CAFI disease develops. Thank you.